In this video, we'll formally introduce the multi-layer neural network. We've seen previously that there are certain problems that a single artificial neuron can not model well because it's a problem which is, say, in a classification setting that is not linearly separable. However, we've seen that we can actually take our input representation and try to instead transform it in some way by applying some perhaps simple transformation, like applying, in this case here, the n function over 2 transform version of the input to obtain a new representation of our input vector, which is now linearly separable. And if the computation of this representation can be made by artificial neurons, then this is suggesting a more complicated model for more complicated problems, which would consist in first computing a set or a number of artificial neurons that will compute this new representation, and then connecting those neurons to an output neuron, which would do the rest of the job and finish the computation of our more complicated function. And so this will be the inspiration behind the use and development of multi-layer neural networks. So let's look at this idea more formally in the case of a single hidden layer. What we mean by the hidden layer is the computation of this representation, which will make the problem more linearly separable. And so in the single layer neural network, we'll have the first part of the computation, which will compute the representation, and then finally the computation of our output unit, which will perform the the computation of our binary classification. So more formally, when we're computing the hidden layer, we will compute again a pre-activation function. And now in this hidden layer we see here, we might have several neurons, not just a single neuron. And so each of the ith neuron, which I will call whose activation function, the output activation, will be h of xi, will be connected to all potential inputs. And so the connection between the ith hidden neuron with the jth input will be contained in some matrix, which we will call W and its exponent in parenthesis 1. So this is to refer to the case where we have just a single hidden layer. So W1 is the weight matrix for the first hidden layer. And similarly, we will have biases. And so the bias of the ith hidden unit will be BI, and the one here in the exponent is to refer to the first hidden layer again. So whenever we are computing the pre-activation, we will actually have a vector of pre-activation where the ith element of that vector will be the ith pre-activation for the ith neuron in that hidden layer. And so for the ith vector, the ith pre-activation will get the ith bias plus the weighted combination of all inputs xj, and where xj will be multiplied by its connection with the ith neuron. And if we want to perform this computation, for each hidden unit, so in fact we can write it into matrix form to obtain directly the pre-activation vector. And this would only essentially correspond to taking the vector x, multiplying it by our matrix W1, and then adding the whole vector of biases B1. So indeed, if we take x and multiply it by W, what we'll get is that for the ith row, we'll get a term which corresponds to the sum of all the elements over that row of matrix W1 multiplied by the corresponding elements in the vector x. Okay, so we see that this and this is actually equivalent. Then to compute the hidden layer activation, we simply apply our activation function over all the elements in the vector. So this here in my notation, I'm assuming we're doing an element-wise application of the activation function j that we've chosen, either the sigmoid or the tanh or rectified linear and so on. And then finally we get an output activation, which I will call, or I will note f of x, by taking the hidden layer. So this hidden layer, so there's a parenthesis missing here, we'll call it h1 of x. Again, 1 because we have a single hidden layer. So we'll take that vector of hidden units and then we'll multiply it by w2, which is going to be the vector of activations between the output and all the hidden units. So w2y here is the weight of the connection between the output unit and the ith hidden unit. So we compute that, then we add the bias of the output unit, and then we will also have a activation function, and I'm going to note it O for output activation function. And this is because we will typically make different choices for the output activation function than for the hidden units in the neural network. So if we want to do binary classification, we can just use as the output activation the sigmoid activation function. And so this would correspond to this means that at the output we would get the probability of the input belonging to class 1. But if we have multiple classes, if we have more than 2 classes, then what we'll need to do is have multiple outputs. And specifically, we'll want to have one output unit at the output layer per class. And now we'll still want to keep this idea that our neural network will estimate a conditional probability. So we'll like the output layer to give us the probability of the input belonging to each potential class, which I note C. So C would typically belong in 1 up to a certain number of classes capital C. Okay. So if we had 10 classes, then capital C would be equal to 10. And so we would have indexed all of our classes from 1 to capital C, 1 to 10. And so to get an output which corresponds to a valid conditional probability, what we'll use as the output activation function is what is called the softmax activation function. And what it takes is that it takes the pre-activation and it simply takes the exponential of all elements of that pre-activation vector. So it's a vector now because we have multiple classes, so we have multiple output neurons, and so we have multiple pre-activation values. So the softmax takes the exponential of all of those numbers and then divides each of these numbers by the sum of the vector, by the sum of the exponential of the pre-activation for all possible classes C. That's why we have a sum over C here. Okay. So because we are normalizing our vector like this, because we're dividing by the sum of the numerators here, then we are guaranteed that it will sum to 1. And that's because we're divided by the sum of the numerators. And also we're guaranteed that it's going to be strictly positive, and that's because the exponential of any number is necessarily greater than 0. So we will have a valid probability distribution because the probabilities are positive and they sum to 1. And then if we want to predict an actual class, so if we get an input X and want to actually assign it to a particular class, then the natural thing to do is to use the class with the highest estimated probability. That is, again, we just look at all the output units and we output the class associated with the output unit that has the largest value. And finally, in the previous example, we had only a single hidden layer, but there's no reason for not using multiple hidden layers. And we will discuss in other videos why we might want to do that. But to get this generalization to multiple hidden layers, say L hidden layers, we'll have now a pre-activation function, a pre-activation value at any hidden layer K. So we'll call that AK of X. And this will just correspond to the bias of that hidden layer plus the matrix of connections for that kth hidden layer multiplied by the activation values at the previous hidden layer, so at the hidden layer k minus 1. And if we use, for our definition, if we assume that h0 of x is just x, so h0 would be the 0th hidden layer, so this will correspond to the input layer here in our definition, then this correctly defines the pre-activation value at all hidden layers. And then to get the hidden layer activation, so the output of the hidden units at each hidden layer, what we do is that we simply apply again the activation function on the pre-activation of the corresponding hidden layer. And then to get our output layer activation, which corresponds to the index of the layer k equal to L plus 1, where L is the number of hidden layers, then what we could, if we use these definitions here for the pre-activation function, so for the layer L plus 1, h L plus 1 of x is going to be again the pre-activation function, but passed through an activation function. For the case that we have the output layer, so the index L plus 1, we'll use, however, not the G activation function, but the output activation function that we're noting O. And typically, instead of using this for the notation of the output layer, I'll often refer to it instead as f of x, which is going to be the output of the neural network. Now, if you're wondering why we say that these layers here are hidden and this is instead the output, so this is the output for the obvious reason that this is the actual value that is used, say, by our classifier, which is trying to classify some input. And these are hidden because we don't know what's the actual right value for these hidden units. So the neural network, when we talk about learning the parameters of a neural network, it will try to find what's the correct behavior for these neurons here. However, for the output, we know what's the right answer. So we normally will have some labeled data, and for some given input, we will actually know which output we want to see have its value be the biggest amongst all output. So that's why these hidden units are actually hidden. They're hidden in the sense that we don't know what's the actual best value for them to take for some given input. We only know what value we would like to see for the output if we actually know, say in some data, if we actually know that certain inputs are classified in some certain classes.